Welcome to Algebra 2, Unit 2, Section 1, Parent Functions. At the end of this lesson, I can construct parent functions and I can identify the domain and range of parent functions. Alright, so parent functions are basic forms of functions. There's actually 12 of them. We're going to discuss 5 of them today, 4 of them right now, and then one later on in the lesson. So the first one we're going to talk about is linear functions, and we've already been talking about linear functions, right? So the rule for linear functions would be f of x is equal to x. So basically this is nothing more than a line that matches up. It's on a 45-degree angle, so we're just going to put this here on our graph. And so the graph of linear functions is always a line. And in this case, this is the parent function, just f of x equals x. Quadratic functions are functions that have x squared. X squared is the parent function. And basically what this entails is what we would call a look such as this. And all quadratic functions are shaped like a parabola. Alright, so due to the fact that anytime we square any number, it's a positive value, you'll see that all the values on our x squared are positive. Our next function is the square root function. We can't have any negative values plugged into a square root. It blows it up. So it looks like this. It starts at 0 and it kind of flattens out and continues on just like this. So this would be the square root function, by the way, is the square root of x. Our last parent function we're going to talk about at this time is the the absolute value of x, which looks like that. That's what that function looks like, the absolute value of x. And what we have when we do this function is, since absolute value is the distance of a value from 0, this function looks just like a letter V. It's very distinct. It comes to a sharp V point. Okay, so the absolute value of x graph would look just like this. Now, in looking at these graphs, we can come up with what the domain and the range of these functions are. So for linear functions, and we've talked about this, the domain is always all real numbers, and if we put this in interval notation, it looks like such, right? From negative infinity to positive infinity. The range is also all real numbers, and so again, in interval function or interval notation, we would end up with negative infinity to positive infinity. For this specific quadratic function x squared, our domain is again all real numbers. It doesn't matter, we can put any real number into this function and it'll come out for us. But the difference is this: once we plug any number into x squared, the range is going to be from y, and the lowest value is going to be 0. So this would be in interval notation 0 to positive infinity. Now here's where it gets interesting with the domain. We have to restrict the domain of the square root. So when we plug this value in, it's got to be greater than or equal to 0. So in this case, we would have 0 to infinity in our interval. And also, because when we plug these positive values in, we're going to get a positive value. So y is going to be greater than or equal to 0 for this function, right? For the square root function. So this is 0 to positive infinity. Our domain, again, with the absolute value of x, is going to be all real numbers, right? and our interval. But our range again is very similar to that of the quadratic in that it's going to be greater than or equal to 0, and so we're going to have 0 to positive infinity. So one of the things we can do is we can take some data and we can plug it in to a graph, and then we can go and figure out what type of the best function. Okay, so we're going to do that. We're going to go to -4, +8, and up here to 8. And then we're going to go to -2, and that's going to take us to +2, and this is 0, 0, and then we're going to be at 2, 2, and we're going to be at 4, +8. And we can see here that even though this is as a discrete, looks like a discrete function here, we can go ahead and connect this with a line. And so that's what we're doing right here. Okay. So the parent function in this case would be quadratic, right? Would be the quadratic function of x squared. The actual function that we see here is actually 1/2 of x squared. Our domain is, as the parent function, would be all real numbers, right? And we would do interval. But our range, again, is going to be y is greater than or equal to 0. And we would have 0 to infinity on interval notation. Okay, with this function, let's go ahead and plot these points again. -2, 6, 2 to the left, 6 down, right here. And then at -1, 3, which puts me 1, 2, 3 right here, and then 0, 0. And then we're at 1, 3, and then at 2, 6. So we can see here we have a nice straight line. We can take this here, there we go, and we have to do this process of getting our ruler to match up here. I find it easier to go this way with it. So here's our line. So our parent function again is linear, right? And that would be f of x equals x. This actual function, f of x, would be equal, our slope is 3, we can see that, right? We could also do some calculations using these values here and finding our slope. So this is f of x equals 3x. Our domain is all real numbers, as is all linear, right? All linear functions. And our range is all real numbers. Okay, so here we have -8, 6, -6, which takes us right here. And then -7, -5, which comes here. And then -4 and -4 comes here. And then we are at 1, -3. And 8, -2. And we can see here, this definitely looks like our square root, right? This looks like the square root function. So the parent is the square root of x. All right, this actual function, and we're going to learn how to do this later, on how to transform these, right? translate actually. So actually this function looks like this. F of x, the square root of x plus 8, and then minus 6 outside of the root. Now, this function, when we look at this function, the smallest x value we're given is negative 8. So the domain here is x has got to be greater than or equal to negative 8. Right? So we would put this in interval form like that. And then our range would have to be greater than or equal to negative 6. Right? And that value would look like this in interval function, right? That's our way of notating this. Okay, so now we're given a bit of a word problem, and what we have is a ball is thrown upward and the data for the height of the ball is shown, right? So graph the relationship. So we're going to take this data and we're going to plot it. So at 1 second, this is 9 meters, so I'm right here. Right, my scale on the left is in 2s. Okay. At 2 seconds, we're up to 16, which is right here. At 3 seconds, we're up to 21, which is right here. At 4 seconds, we're up to 24, which would be right there, right here. At 5 seconds, we're right here at 25. All right. At 6 seconds, we're at 24 again. At 7 seconds, we're back down to 21. Okay. So, we definitely have a parabolic shape here, right? That's starting off, and this would actually come all the way down like so and land somewhere like this, right? So, and I didn't draw this. Well, I didn't draw it terribly, but we'd be better off with this right about here, right? This needs to come out here like this, right? And at 8 seconds, I need to be right about here. Oh, now I'm off. So we're going to fix this real quick. I make mistakes too. So this needs to be here at 8, and this needs to be here at 9, and then hit the ground at 10. Okay. So what we have here is a ball that traveled that path. It's a parabola, right? So this would be best served with a quadratic, right? This is a quadratic. And the interesting thing is, this is when things are thrown in the air, shot in the air, fired up in the air. This is the study of ballistics, right? And the study of ballistics, first word is ball, because ballistics used to deal with how cannonballs were fired and the path they took, right? All right, so let's go to this here and say use your graph to estimate the height of the ball at 8 seconds. Well, at 8 seconds, this should be right about here, right there. All right. So at 8 seconds, right, it should be at 16 feet. So at 8 seconds, we'll be at, or 16 meters. I should use the metric system. This is a mathematics class, right? So we use metric mostly. Okay. Now let's take a look at the next one. It takes a pendulum. The time it takes a pendulum to make one complete swing back and forth depends on how long the string is. So over here we have, this is string length down here. And this is time in seconds. So let's plot this. At 2 seconds, we're at 2.8, right? Or at 2 meters in length, it takes 2.8 seconds. So here's 1, here's 2, and that's going to be approximately here. At 4 seconds, we're at 4. At 6 seconds, we're at 4.9. It's just about here. At 8 seconds, we're at 5.7, which is just about here. And at 10 seconds, we're at 6.3. So right here. Now, keeping in mind at 0 seconds, right, this would have to come down to 0, right? At 0, no string length, there's no time. So technically, our graph would travel this path here. And it's very evident when we put a ruler to this that there's a curve here, right? It might become very difficult to even see right here, but there is a bit of a curve, right, from here to here. See? So it's not a straight line, so sometimes using a straight edge will help discern what we have. So the square root function, all right, a form of the square root function would be what's best. All right, so for the pendulum to take 4.5 seconds to make a complete swing. So I'm going to use my ruler here just to do a little help work here. And I'm going to see that at 4.5 seconds, there's about 4.5 seconds right there. So at 4.5, I hit the graph right here, right? And lo and behold, you can see as you come down this straight line here, this puts me at 5 seconds, right here. So, or 5 meters, excuse me. So that would make a complete swing. At a 5-meter pendulum, or a 5-meter long pendulum would take approximately 4.5 seconds to make a complete swing. Alright, so we're going to look back now at our parent functions. And what we're going to do is we're going to look at some data from those functions, plug some things in and see what we get. Right? So let's plug a couple numbers in. Let's do 5 of them. So I'll say like -5 and -2 and 0 and 2 and 5. Well, what happens here is I've got -5. The absolute value of -5 is +5. The absolute value of -2 is 2. 0 is 0. 2 is 2. 5 is 5. So I end up with a graph that looks like so. Right? So if I take my ruler out now and I connect these dots, I end up with very nice rendition of the graph of f of x is equal to the absolute value of x. Alright, let's take a look at x squared. Alright, so we'll take a couple, we're going to take smaller numbers on this. Alright, so let's go -2 and -1 and 0 and 1 and 2. Let's see what we get. Well, -2 squared is +4, -1 squared is +1, 0 is 0, 1 is 1, 2 is 4. So we end up with a graph that looks like this, right? And we can see here we have got our parabola. Now, when doing this type of thing with square roots, I find it a lot easier to go in reverse to come up with x values. And you might think, well, that's not right, but it does make it easier to do. So I'm going to plug in. First of all, I can't put any negative values in. So I'm going to put in 0, 1, 2, and 3. So 0 squared is 0, square root of 0 is 0. 1 squared is 1, square root of 1 is 1. 2 squared is 4, so the square root of 4 is 2. And 3 squared is 9, so the square root of 9 is 3. So now I can go ahead and plot these points. So 0, 0, 1, 1, 4, 2, and 9, 3. And here's our graph. Alright, here's one we have not seen yet. X cubed. So we'll put in -2, -1, 0, 1, 2. So -2 cubed is -2 times -2 times -2. Well, -2 times -2 is +4, but +4 times -2 is -8. -1 cubed is -1 times -1, which is +1, times -1 is -1. And then 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. So this is a rather interesting graph, because what you're going to see is as -2, -8, 1, 2. That's down here. This is here. This is here. This is here. And then this one goes up here. So we end up with a situation where this graph crosses over like such and then curves back down. Okay, and this is a parent function. This is called the cubic function, right? The cubic. It's like a cube, 3 times something, but something multiplied by itself 3 times, right? So you'll see it crosses over and then moves up, right? So cubic functions operate this way. They cross over, all right? And they have this very specific type of shape. All right. Well, f of x equals x, that's pretty basic again, right? Let's go -5, 0, 5, because we know that this is our line, right? So it's a 45-degree angle line on this graph. And we can see that matches up, and we're just going to put it in there. I'm not even going to plot those. Okay. Now, this situation is very interesting. You're looking at this, go, wait, this function always equals the same number. So the same number, no matter what I put in for x, y is always going to be 4. So if I put 5, negative 5, excuse me, y is 4. If I put in 0, y is 4. If I put in positive 5, y is 4. It doesn't matter. No matter what you plug in for x, y is 4. F of x is 4. So this is going to look like this. So here's a hint. What kind of line is this? This is a horizontal line. So anytime you get a function that's just equal to a number, okay, all right, it's going to be a horizontal line. So that concludes our conversation for today about parent functions. Have a great day. Peace.
That's all, folks.